Good morning, everyone. Welcome to my presentation. Today, I'll be presenting our paper, OblivGNN, so Oblivious Inference on Transductive and Inductive Graph Neural Networks. So my name is Zhibo. It is a collaboration with my supervisor, Professor Xingliang Yuan from the University of Melbourne, and Dr. Shangqi from the CSIRO's datasets Yuan, as well as our collaborators, Dr. Xiaoning from the RMIT University, Dr. Alsharif, Abuadbba from the CSIRO's datasets Yuan, and Professor Xingliang from the RMIT University. So graph neural networks, or GNN, is a special neural network architecture designed to operate on graph structure data. There are mainly three tasks: node classification, graph classification, and link prediction. And today we'll be talking about the node classification. So node classification refers to the use of GNN to classify the nodes into a particular category or class. The client sends the node ID to inquire the node class, and the server returns the inference results to client. Because of its popularity, it's increasingly featured on MLaaS platforms such as Amazon, Google, and Microsoft. It uses typical two stages, training and inference phase. For GNN inference services on MLaaS servers, the GNN model will be loaded onto the server and let user to upload the graph for inference. Today, we'll be focusing on the inference service for GNNs. Because of its outsourcing nature, if the inference services for GNN on the MLaaS platforms are computed without protection, we'll have the following two main privacy concerns. One is the leak of client's sensitive information. So graph information usually contains large amount of resources to collect. For example, it could be the sensitive chemical structure in drug discovery or the client's financial transaction histories in bank fraud detection systems. The second is the bank is leaking its proprietary model, which always considered a private IP to the cloud service. To solve the above privacy concerns, there are previous endeavors called privacy-preserving machine learning to try to protect the machine learning services, such as the inference service, on the cloud. However, there are two problems. The traditional PPML frameworks cannot support graph structure data, and the existing secure GNN frameworks do not offer full protection on the graph structure data, such as leaking the graph degree information. And they do not support the diverse setting of the GNN, which I'll be talking about in a minute. And they also use heavy cryptographic tools that incur high costs. So before we dive into how to address this existing issue, we first need to know exactly what exactly is a GNN. So a GNN is typically defined as a two-layer neural network architecture, which each layer consists of an aggregation and a activation. So in the model forward propagation, the A representing the adjacency matrix and the F representing the feature matrix. And the W is the model weight matrix. After aggregation using AFW, the two activation functions, ReLU and softmax, will be used to further extracting the graph information. So after we talked about the GNN and the node classification, let's talk about the two unique settings of the GNNs, transductive and inductive. So transductive setting means the training graph contains both the labeled nodes and the unlabeled nodes. And the inference will be the client inquiry the node's ID and retrieve the node's labels. The inductive setting means the training graph only contains the labeled nodes without knowing the unlabeled nodes. The inference will require the model to run the prediction on the updated graph or newly updated edges before running the inference for predicting the node's labels. To build the secure GNN that runs on both transductive and inductive setting, there are many building blocks. And due to the time limitation, I'll be talking about the two main building blocks here. So distributed point function. So distributed point function and the arithmetic function secret sharing. Both of them are categorized as FSS. The only difference is their utilities. The DPF refers to share a point function in the form of keys to two parties, and the two parties will collaborate to evaluate and return the result in shares. The result will be the beta only if the alpha x equal to alpha, otherwise 0. And similarly, because the DPF characteristics, we can use it to perform a secure equality testing and comparison for activation functions. The arithmetic FSS on the right-hand side uses random numbers masks R in 1, R in 2, and R out. They're used for key generation and evaluation on the masked inputs. The evaluation process will return the multiplication or addition result in masked shares. The distributed point functions can be used in secure extraction of the node labels from the inference result, and the DPF equality testing and comparison can be used in secure activation functions. The arithmetic FSS will be used to build the secure aggregation, which we'll be talking about in short. So transductive setting, to realize the secure GN, we now have our strawman approach. The client feeds the graph into the model, and the model propagates and returns the inference result to the client. The entire process is secured. The client uploads the graph in secret shared form, and the secure aggregation is done by using Bevis triples. In regards of the secure activation, it is done by polynomial approximation. It is secure but simple, but there is an issue. The graph is static and cannot undergo updates. Therefore, to update the graph, the client can renew the graph nodes by nodes by feeding into the model. Now we notice another problem. Because the graph is represented in matrices, if we update the graph, for example, adding nodes or adding or updating the edge, which is essentially adding or updating a particular row or column in the matrices, even it is in encrypted form, such access pattern leakage can still be exploited for the leakage attack if it is compromised. So now we have our final form of the strawman approach. The client can update the graph by simply re-uploading the entire graph to the model for inference. The access pattern is now protected. We call it oblivious. But now new problem here is because we are re-uploading the entire graph, the computation and communication is significant. So we have 3 research questions that needs to be addressed. So the first one is how to enable the secure GN inference for the transductive and inductive setting, and how to offer data obliviousness with semi-honest security, and how to achieve the efficiency while achieving the above. So we propose our approach, so OblivGNN. The OblivGNN architecture has the following characteristics. We consider semi-honest adversary. It is an outsourced model, and we assume that servers are non-colluding. The model owner possesses a GNN model that wishes to leverage the OblivGNN to enable the oblivious inference without revealing the model. The client is the querier who requests an oblivious node classification to the OblivGNN. It submits the node ID or the graph to the OblivGNN and receives the inference result without revealing its private query. 2 cloud servers in different trust domains obliviously execute the inference without seeing the model or the graph in clear text. We guarantee to protect the graph information, the model information, and because we need to update the graph without leaking the access pattern, we also need to protect the graph structure and features. After inferences, we also protect the client inquiry, any intermediate result, and the inference results. The OblivGNN has 2 stages, offline phase and online phase. The offline phase is responsible for masking the graph inputs and generating the DPF and FSS keys for the online phase accordingly. The online phase is 2 servers running the oblivious aggregation and activation for 2 layers and yielding the inference results. If it is an inductive setting where the graph needs to be updated, the clients will first obliviously update the graph before running the oblivious inference. First, let's talk about the offline. So we first need to mask the GNN model. We use 3 sets of masks for both masking and arithmetic FSS key generation. They are masks in 1, are into, and are out. To perform the oblivious aggregation on 2 servers, the servers needs to be recovering the masked ASS shares before the FSS circuits. The linear layer result shares can be used in oblivious activation function, and in an inductive setting, the oblivious updates are also performed on the shares. Another job on the offline phase is the generation of the keys, so the FSS and DPF key pools. The FSS key pool consists of multiplication and addition gates. The DPF key pool has the online keys for graph updates and the client inquiry, because these keys can only be generated when they are in demand. And in the offline phase, for the oblivious activation functions, we will need to use the DPF equality testing keys and comparison keys. Let's now have a look on how to use the FSS keys for the oblivious aggregation. As shown in the figure, the masks are carefully chained together because some of the R out are actually fed in as the next layer are in. The FSS key generation is also performed in such a way to ensure the entire oblivious aggregation are done correctly. The FSS evaluation are performed layer by layer to construct the oblivious matrix multiplication. Similar operations are repeated for the weight matrix. After that, the first layer of aggregation is done. For the sake of time, we are not going to dive deep into the oblivious activation functions here today. We refer to the previous works from the Raphael et al., Marcel et al., and Keller et al. With the minor modifications. Please refer to our paper for the details. For the inductive setting, we have two more operations. The first one is the insertion of new nodes. The second is updating on the existing graph. And for the node insertion, it's very simple. We just simply append the new nodes at the end of the adjacency and feature matrix. However, the existing graph update is more complex. To update the adjacency matrix, we will need to use the online generated DPF keys for the client. To perform a full domain evaluation for the node in each row and each column that requires an update, from the given example, the places 0, 1, and 1, 0 needs to be updated from 0 to 1. Therefore, the DPF keys are generated with the location information and the updated value information. Because of the characteristics of DPFs, the evaluation is a linear scan through the entire domain. Therefore, only the correct places where the 0, 1, and 1, 0 will be updated with the 1 shares, everywhere else will be updated with the 0 shares. Similarly, the feature matrix can be updated using the same methods. Now we have successfully performed the graph updates using the DPF keys, and we have now achieved both obliviousness and efficiency. Last but not least, the client can retrieve the inference result by submitting its query DPF keys. Two servers will be performing a linear scan for each node and returning the client with the masked result in shares. For example, the user queried the nodes once label. He first generates the DPF keys, and each server evaluates the DPF keys for all nodes. Only the node 1 can be evaluated with a 1, and everywhere else is a 0. The client can then combine the shares from the result and demask for the plain results. This is a direct application for DPF, so we call it private information retrieval. It not only protects all the nodes labels, it also protects the access pattern when retrieving the inference result. Our experiments are done in Python and C++. We use 3 datasets, Cora, Citeseer, and Pubmed. The baseline will be the pure additive secret sharing for inference. And our results are promising. So we achieved a system runtime with an average reduction of 38%. Because of the advantage of the linear layer, the larger the graph, the more time can be saved from the matrix multiplication. We also achieved a reduction ranging from the 10 to 151 times in the system communication. The advantage is taken from the employment of arithmetic FSS instead of the Beaver's triples. We also achieved a logarithm growth towards larger graphs. It is because the key size in the DPF full domain evaluation has a logarithm growth. And that is all. Now it's Q&A time. Thank you.